Before we are going into the net flux into the controlled volume equation, we can simplify the equation number 8 as well as 9 and 10. And the simplified equation is the d by dx of rho w into qx into delta x into delta y into delta z and d by dx of rho w, d by dy of rho w into qy into delta x into delta y into delta z, and d by dz of rho w into qz into delta y into delta z. These equations, that is number 8, 9 and 10, is the simplified form of these equations, such as for example the d by dy rho w into qy into delta x into delta y and into delta z is obtained by cancelling out these two, and by we'll get this equation, and in the same manner we will get the d by dx into rho w into qx and delta x and delta y into delta z, as well as from the equation 10 we will get the simplified equation, that is d by dz into rho w into qz into delta x into delta y into delta z, that is the equation number 10, which is simplified from this by cancelling out these two components. So next we are moving on to the net flux equation of the controlled volume. For getting the next net flux equation, we will add all the three equations, that is 8, 9 and 10. Then we will get, in this equation we have the minus sign also. So the equation will be minus of d by dx into rho w into qx into delta x into delta y into delta z, and minus d by dy of rho w into qy into delta x into delta y into delta z, minus d by dz of rho w into qz into delta x into delta y into delta z. This becomes the equation number 11, that is the net flux equation for the controlled volume. And next we have to consider the right hand side of the mass inflow minus mass outflow equation mentioned in the seventh equation. That is, in the seventh equation we have mentioned mass inflow minus mass outflow is equal to the change in storage with respect to the time. So next we have to consider the right hand side of this particular equation. This is just the left hand side, that is mass inflow minus mass outflow, that is equal to the net flux. So the right hand side of the equation, that is the change in storage with respect to the time, will be is equal to, that is the right hand side of this particular equation, which is equal to the d by dt of n into rho w into delta x into delta y into delta z. So this right hand side portion represents the change in storage with respect to the time, and we will number it as 12. And according to the equation, so we have to equate these two equations. So the form of particular equation will be d by dx into rho w into qx into delta x into delta y into delta z minus d by dy of rho w into qy into delta x into delta y into delta z minus d by dz of rho w into qz into delta x into delta y into delta z equal to the change in storage with respect to the time, that is d by dt of n. N means the porosity and rho w is the density, delta x and delta y and delta z is the change in length or in all the three axes, and this is the equation number 13. This is the equation number 13, and next is dividing this equation number 13 by delta x, delta y and delta z on both the side. Okay, then we will get a simplified equation like d by dx of rho w into qx minus of d by dy into rho w into qy minus of d by dx of rho w into qz. So what we are done is dividing the both side by means of delta x into delta y into delta z, dividing equation number 13 by delta x into delta y into delta z. Then we will get this particular equation, and which is equal to d by dt of n into rho w, that x, y, z, the delta x, delta y, delta z component will be cancelled out, and we will get a simplified equation like this, and we will number it as 14. Next is, this is n into rho w. Next is, we have to expand the right hand side by means of the product rule. So we will get the equation like this: d by dx into rho w into qx minus d by dy of rho w into qy minus d by dz into rho w into qz is equal to, according to the product rule, the right hand side will be n into d by dt of rho w plus rho w into dn by dt, and this is the equation number 15. So what we are done is this right hand side is expanded by means of the product rule, and this right hand side portion, that is n into d by dt rho w plus rho w into dn by dt, can be written in other form like rho into rho w into g into alpha plus n beta. This particular equation can be rewritten like this, because in which the alpha represents the compressibility of the aquifer material, and beta is represented by the compressibility of the particular fluid. And if you take the product of density and acceleration due to gravity and alpha plus n beta, we will get the equation of specific storage, and the right hand side equation can be rewritten in terms of the specific storage equation. That is, this can be rewritten as SS into rho W into dH by dt. So alpha is the compressibility of aquifer, beta is compressibility of water. So this equation can be rewritten in terms of the specific storage into the density into dH by dt, where the dH is, or the dH is the hydraulic head and dH by dt is the hydraulic gradient. So we can rewritten the right hand side as like this, and this particular equation is numbered as equation number 16. And by substituting the equation 16 into the equation 15, so we have to substitute this SS, specific storage, into the density into dH by dt into the equation 15. So we will get minus of d by dx into rho w into qx minus d by dy of rho w into qy into minus d by dz of, just erasing this portion, rho w into qz is equal to ss into rho w into dH by dt, where the dH by dt is the hydraulic gradient. This is the hydraulic gradient. Hence we will get the equation number 17. And next is, in this equation number 17, we know that the rho w is a common factor, so we can rewritten the equation number 17 as minus of rho w into d by dx of qx minus rho w into d by dy of qy minus rho w into d by dz of qz, which is equal to ss into rho w into dH by dt, which is equation number 80. So what we are doing is, what we are done is, this common factor, that is the rho w, is taken out from this, and in all cases. So next step is, the density is common in both, rho W is common in both the right and left hand side. So the the rho W can be neglected, or it can be eliminated from both the side of this particular equation. Then the equation will be because the reason for eliminating this rho W is it is the effect of change in density will be negligible. So we are eliminating minus the rho W from the equation number 18. So we'll get a simplified equation like d by dx of qx minus of dqy of dy minus d by dz of qz is equal to specific storage into this rho W will be eliminated, neglected, so dh by dt. This is equation number 90. Okay, and next is based on the Darcy's law. According to the Darcy's law, the Qs, that is the discharge, is minus K into dH by dt, where Q is the flow per unit cross-sectional area and K is represented by the hydraulic conductivity and dH by dt is the hydraulic gradient. So according to Darcy's law, we can write Q as minus kh into dh by dt. So we can rewritten all the qx, qy and qz in terms of this equation, like qx equal to minus kx of h divided by dx, and qy is equal to minus ky into dh by dy, and qz is equal to minus of kz into dh by dz. These are numbered as 20, 21 and 22. Okay, and next equation is the putting all this qx, qy and qz into the equation 90, that is putting 20 and 21 and 22 into the equation 90. Then we will get the equation like d of minus of d by dx of minus of k minus, and this minus will give the plus sign, so we can write as d by dx of kx into dh by dx plus d by dy of ky into dh by dy plus d by dz into kz into dh by dz, which is equal to ss into dh by dt. So this become our equation of groundwater flow of an heterogeneous and anisotropic aquifer. So this become our differential equation of groundwater flow in heterogeneous and anisotropic aquifer. So this become our final equation, and this equation representing the differential equation for the groundwater flow in an heterogeneous as well as the anisotropic aquifer. And this equation can be rewritten in terms of the transmissivity. So if we want to, or if you like to write this equation